So our topic for today is going to be section or unit 1.3, day 4, which now we're going to be talking about geometric and arithmetic series. So series is going to be this new word that we're going to look at, and we're going to see how that applies to what we already know. So the first thing that we have always been kind of doing is kind of stating our objective. And so today our objective is that we're going to find the sum of the first n terms of a finite series. So series we're going to define in just a minute. But finite just means that it can be counted. So really what that is basically talking about is you think of the word infinite means goes on forever. Finite means that it can be counted, it will stop eventually, and we won't have to, keep guessing on what it's going to stop or anything like that. So it's just finding the first n terms of a finite series. And so the first thing is that we want to look at what is a series and how does it apply to what we're doing. So a series is the expression for what we call the sum of the terms of a sequence. And so the idea is that the sum is represented by kind of a new notation, which is S sub n, which basically means the series of any number of terms that we want. But the idea is that this is the sum of the terms of a sequence. So for example, if we see a sequence, it would look like this: 1 plus 2 plus 3 plus 4 plus 5 plus and on and on and on. And as if you can see this, as we're going here, we're adding 1 every time as we go from number to number, not necessarily looking at the addition. But what we're basically doing is we would take that sequence that we already know and then just basically add up all the terms to those, and that's what we call a series. And so it's the expression for the sum of the terms of a sequence. And so we can start off with, what does a series look like? And so we have two different series. We have our arithmetic series and we have our geometric series, just like we have our arithmetic sequence and our geometric sequence. The idea is that everything is still the same. And so when you look at these formulas, again, formulas are just formulas because we're going to plug in all the information that we need into our formula and be able to find it. So when we look at what is needed, when we have our arithmetic sequence, we have a sub 1, we have this and this n, and that's really all that's needed for an arithmetic series. And so if we remember a sub 1, that's our first term. So all that we need to know in an arithmetic series is our first term. And n would be the number of terms that we want. So if I want you to tell me the first 50 terms and what they would add up to become, all you would have to do is plug that information in. Now, the last piece of information, a sub n, what that's going to end up being is that's going to be our last term. So basically, when we look at this, we have our first term, we have our last term, and then we take how many times that we did that and divide it by 2. So we're basically kind of taking all those terms, adding them together. We know what happens in between all of them, and so we're just kind of adding that together. Now with our geometric series, it's a little bit different, but really not anything too crazy. But the idea is that we need a sub 1, which again is our first term, and we need r, which we know is our constant ratio, and then the last thing that we would need would be our n. So basically what we're going to need to know is our number of terms that we want to use. So similar to what we did over with the arithmetic sequence, we're going to need to know our first term, we're going to need to know our constant ratio, and then the number of terms. And so after we do that, we're basically just plugging this information in. So it doesn't matter what it kind of looks like. Basically this is just going to come down to a particular value, and that value is going to be the sum of all those terms. And then we'll talk about eventually why we do this and why we need that. But the idea is, as of right now, we have an arithmetic series and we have a geometric series. We have a formula for the series. We have a formula for the series. We just find those pieces of information that are missing, plug them in, and then we solve them. And so we're going to look at a couple examples of how that works. And so the first thing that we're going to look at is we're going to look at an arithmetic series. And so if we look up here, I'm just going to keep this formula up here so that we at least have it in front of us. And then here we have a sequence in kind of a series that it's in front of us. And so when we look at this, the first thing that we need to do as far as our steps are concerned is we need to determine whether this is an arithmetic or geometric series. Because in some cases, it might not actually be an arithmetic series, and then we wouldn't have to do anything with it. Or it might be a geometric, and then we would have to do something different. So the first thing is we're going to determine whether it's an arithmetic or geometric series. And so all I'm going to look at is I'm going to look at these values. I'm not going to worry about the addition in between, but I'm going to look at the values specifically. So as I go from -5 to -7, I'm minusing 2. And as I go from -7 to -9, I also minus 2. So what that tells me is that tells me my common difference is -2. But if you notice in our formula, we don't actually need our common difference because all that we need to do is just use the correct formula. So, in this case, I need to find 3 pieces of information: n, a sub 1, and a sub n. And so I'm going to go ahead and do that. So I would look at n. So the number of terms that I want is I'm going to look at 8 terms. I need my first term, which in this case would be -5. And then I need my last term. Now this is where I'm going to have to use some of my other sequence stuff where I'm going to have to go and find my 8th term. So even though it's not specifically in the equation, I actually have to go and find that. So I need to find a sub 8. And the way that I do that is using my explicit formula. So I use my explicit formula, -5 plus 8 minus 1 times -2. Now if you don't remember your explicit formula, a sub n equals a sub 1 plus n minus 1 times d. So I still need to have some of that information. I plug that in, and I follow my order of operations, and I get -19. So that tells me that my last term, my a sub n, would be -19. Because I told you we need to find our first term and we need to find our last term. So now all that we need to do is plug in this information to our series. So the series evaluated to 8 terms, so the series added to 8 terms, would be 8 divided by 2, because I'm using 8 different numbers, times my first term, which is -5, plus my last term, which is -19. And then I just follow my order of operations with that. I can simplify this a little bit to 4 times -24, -5 plus -19, and that ends up giving me -96. So basically what this is saying is that if I was to add all the terms of this given sequence here, so if I was to add the terms of this sequence here up to the 8th term, I would get -96 when we add them all together. So we're kind of using, if you look at this, we're using some of the elements from what we used before. Obviously I use my explicit formula here to find my last term, because the whole idea is that I need to use that to go and find my last term. Alright, and the same thing is going to happen with this one. So first of all, I'm going to determine whether it's an arithmetic or not. So we go from 3 to 6, that's +3. I go from 6 to 9, which is +3. And I go from 9 to 12, which is +3. Another way that I could do this if I didn't see it very easily, similar to what we did with our constant ratio, I can actually subtract these values so that in a way I could take 6 minus 3, and that gives me +3. But either way, that gives me a common difference of 3. My first term, which is my next piece there, would be a sub 1, which is also 3. Not the same 3, but just a different 3. The n, so I need to find n as well, so I'm down here at step 2, which I'm asking for the 100th term, so that means n is going to be 100. Now the whole idea here is that I need to have my first and I have to have my last term. So I'm going to go and find my 100th term. So I'm going to use my explicit formula from the previous sections. So a sub 100 equals 3 plus 100 minus 1 times my common difference of 3. Multiply that out, and then add that together, and that gives me 3 plus 297, which gives me 300. So my last term is going to be 300. So when I plug this into my series, so the sum of all of my terms to the 100th term is equal to 100 divided by 2 times my first term, which is 3, plus my last term, which is 300. And so once I multiply that out, I can simplify just a little bit. So 50 times 303. And that gives me a final answer of 15,150. So if I was to add up the first 100 terms of this given sequence here, so I look at this sequence here, if I was to add up the first 100 terms, I would get 15,150. So the idea with this is just finding your information, using your explicit formula to go and find that last term, and then basically just substituting everything in and then calculating. We don't really need to make this a little bit more difficult than it is. Obviously, we're going to go over some of this stuff, but the idea is you're using a formula, finding the missing pieces, and plugging them in. Okay, and so the same thing is going to work with what we would consider a geometric series. And so the idea is that we still have our formula. It's a different formula, and so we just have to find different things. So first of all, we just needed to decide whether this is actually a geometric series. And in the process, we're going to find part of step 2, which is to find r. And so the idea is that we have to kind of look between the lines here. So we go from 1 to -3. We go from -3 to 9. And then we go from 9 to -27. So we have to kind of look at what's happening there. But like I told you, you could take two values, divide them, -3 over 1, and that gives you -3. And if you really look at that, I'm multiplying by -3 every time. So 1 times -3 gives me -3, and then +9, and then -27. And so with the geometric series, it's actually a little bit easier because I don't have to worry about going and finding my last term, because with multiplication, we don't have to worry too much about that because we can talk about how many times we're going to multiply. So really, once we find n, a sub 1, so our first term, and r, we're already ready to go. So the first thing is I already have my r, which is -3. My a sub 1 is going to be +1. And then my n is going to come from this part right here, which I want to find the sum of my first 24 terms. And so that means that n is going to equal 24. Plug this into my series. And so in the same fashion that I did with the arithmetic, s sub 24. So that means the sum of the first 24 terms of this series is equal to my first term, which is 1, times 1 minus r, so -3 to the power of 24, and then big parentheses, divided by 1 minus -3. Now this is a little bit tricky as far as how we can plug this in, but the idea is that we can use a fraction in our calculator. We can simplify this by any means, but the idea is we're just simply going to evaluate this. And we can kind of evaluate some of the things that might be a little easier. So 1 times anything is just 1. So we have in parentheses 1 minus -3 to the power of 24. And we're going to keep that like that. We're not going to worry about that one. And at the bottom, 1 minus -3 is actually +4. So I'm going to simplify this just a little bit so that when I calculate this, I'm not doing anything too drastic. And I'll show you how to calculate these in class. But the idea is I evaluate this. And as you might imagine, geometric sequences as they kind of go together are going to become either really large or really small, and I'm going to end up with -7.1 times 10 to the 10th. So this is going to be a very large negative value. But the idea is that we're just following the formula. So with our series, our geometric series, we're looking at what the 24th term is. We're finding n, which is 24. We're finding r, which is our constant ratio, which in this case is -3. And then we're just looking at our first term. And because of the way that this is all set up, this allows us to immediately find the sum without hand calculating this. So we don't have to write out all 24 terms and then add or subtract them depending on how it is. We can use this formula to help us find those as long as we remember how to find the pieces that we need. Alright, and so the thing that we're going to do again is we're going to find if the sequence is arithmetic or geometric. Now this one is a little trickier, And so we go from 1/2 to 1/4 to 1 over 8. And so in some cases we can use our division, but what we can also do is you can kind of set these up. So as I go from 1/2 to 1/4 to 1 over 8, look at the numerator and the denominator. So what's happening between the numerators? Nothing is really happening, except I'm multiplying by 1. And if you look at the bottom, what am I multiplying in the denominator? Well, I'm multiplying by 2 every time in the denominator. So basically what that sets up is instead of dividing those fractions, which would be a little bit easier, we can just look for the pattern. So we're multiplying by 1 every time in the numerator and multiplying by 2 every time in the denominator, and that sets up a fraction of our constant ratio of being 1/2. So when we look at this particular sequence, we can see that we're dividing by 2 every time in a way because it's in the denominator, or we can say we're multiplying by 1/2. So this is the piece of information that we're looking at. So if you need some practice working on finding R, then you need to work on finding R. But as of right now, we can just follow the pattern. If I wanted to divide the fractions, be 1/4 divided by 1 over 2, or 1/4 times 2 over 1, which would give us 2 over 4, and then 1/2. So that we could do either one, but the idea is knowing your patterns, following your patterns, and kind of looking at it through there. So the idea is that now we have our R, and we just need a couple pieces of information. So our R is equal to 1/2. We still need our N, which it tells us our N is 15, so we're going to 15 terms, so we're adding all these up to 15, and then we need our first term. And our first term in this case is also 1/2. Now that we have this, we can just follow our formula. So the series evaluated to 15 terms is 1/2, because that's my first term, times 1 minus, and I'll put this in parentheses, 1/2 to the power of 15, because that's our N. Close parentheses, divided by 1 minus 1/2. Now, this one is going to be tricky to evaluate. When we look at this in our calculator, I'll show you, on our next class period, that what we're going to do with this is, we can set this up in our calculator in a certain way, because this is a little bit, troublesome to try to do. Now, you could use fractions for this, or you could use decimals for this instead of 1/2. You could use 0.5 very easily, but if it wasn't 1/2, we would have to try to do something different. So as of right now, we're just going to evaluate this. We have our formula, and then I'll be able to give you the answer here in just a second. Now, for the purpose of this explanation, what we would get if we want to have something a little bit more tangible is that we would get the following value. And so this is something that we can talk about, but as you can see, we're very close to 1. And this is kind of an approximation. If we were to get the fractional form, it would look like this: 32,767 over 32,768. So if you look at that, there's not a whole lot of difference between the numerator and the denominator, and you might assume that as we go a little bit further, we're adding a little bit more and a little bit more and a little bit more. So the idea here behind these geometric and these arithmetic series is that we're using these to kind of just find the sum, and we'll work on some situations in which this may be useful. But for now, that's going to be it for looking at our arithmetic and our geometric series.